This is the debugger dashboard, a three-panel view of what's actually happening inside the 8085 microprocessor as it executes a program. On the left is our code. The center holds the CPU's internal registers and status flags, and the right contains the memory array. Let's start with data movement. The instruction MVI-A45H loads the immediate value 45 hex into the accumulator. Then MVI-B30H places 30 hex into register B. These operations move data between locations without changing any of the 5 status flags in the flag register. When we execute an arithmetic instruction like add B, the processor adds the content of register B to the accumulator, updating register A to 75 hex. The CPU then uses the flag register to evaluate the result. Since 75 hex is non-zero and fits within 8 bits, the 0 and carry flags remain at 0. This creates 2 distinct channels of operation: data moving between registers and memory, and arithmetic operations triggering physical status switches in the flag register. To perform multiplication on an 8085, we have to use successive addition, adding 5 to itself twice to get 10. This requires a loop skeleton. We initialize a counter, perform the addition, decrement that counter, and check if we need to repeat. In the first pass, we add 5 to the accumulator. Then, the DCRC instruction reduces our counter from 2 to 1. We use this register to track our progress through the loop iterations. On the second pass, the accumulator reaches 10, or 0A hex. When DCRC decrements the counter to 0, the processor automatically sets the 0 flag to 1. The JNZ instruction, jump if not 0, checks this flag, sees it is now set, and stops the loop. To navigate subroutines, the call instruction saves the address of the next instruction onto the memory stack. This allows the stack pointer to track exactly where the program must return once the subroutine finishes. Since the 8085 hardware lacks a dedicated multiplication chip, we combine simple addition with these flag-dependent jumps to perform more complex calculations. Indirect addressing lets us treat register pairs as pointers to specific memory locations. By loading 2050 hex into the HL pair, we aim the processor at a specific address in the memory grid. While a direct command like LDA 2050 reads memory in 13 clock cycles, using the HL pointer with move A, M accomplishes the same task in only 7. The INXH command advances the pointer to the next memory address without altering any status flags. We can then use a second pointer pair, like BC, to store that data elsewhere using the STAXB instruction. Using pointers allows a single block of instructions to scan through thousands of memory locations by simply incrementing the register pair in a loop. Binary math can create issues when working with decimal numbers. Adding 98 and 37 in binary-coded decimal results in CF hex, which is not a valid decimal digit. The DAA instruction corrects this by checking the nibbles. Because F is greater than 9, it adds 6 to the lower nibble. Because the upper nibble, D, is now also over 9, it adds 6 again. This adjusts the result to 35 with a carry, representing 135 in decimal. To calculate a precise time delay, we count individual t-states. Try to calculate the execution time for this 10-iteration loop, keeping in mind that the branching instruction behaves differently on the final pass. The first 9 jumps take 10 cycles each, but on the 10th pass, when the 0 flag is set, the jump is not taken. This final branch only consumes 7 cycles, for a total of 154 states. Understanding exactly how many clock cycles a decision takes allows us to build precise timing delays for hardware communication. For our final challenge, we will scan a 5-item memory array to isolate the largest number. HL will act as our pointer, while register C tracks the remaining items. We load a number, advance the pointer, and subtract the next memory item. If the next number is larger, the subtraction generates a borrow, which sets the carry flag. We use this flag state to decide whether to update our maximum value. This search algorithm is constructed entirely from basic pointer movement, subtraction, and flag monitoring. Debugging these commands requires tracking which operations ignore status flags entirely. Data transfers like MOV and LXI never change flags, while pointer math like INXI ignores the carry flag even if the register pair wraps around. The physical board layout reflects these logical paths. The trace lines and integrated circuits handle the data transfers and branching logic we've analyzed. By tracking these pointer paths and flag states, you can step through and debug the execution of any embedded system.